Hi everybody, welcome back. This is Unit 7, Lesson 2, and we're in Section 2 of our gases notes. Today, today we're going to be talking about vapor pressure and how we can determine vapor pressure and what the difference between evaporation and boiling is. So I thought I'd show you a little video clip or animation on evaporation and how vapor pressure is created, and then we'll talk about the difference between them and fill in our notes.
This is an apparatus for measuring the vapor pressure of a liquid at a given temperature. The U-tube attached to the flask contains liquid mercury, which is used to measure a change in pressure. What happens at the molecular level during evaporation? In the beginning, the traffic is only one way. Molecules are moving from the liquid to the empty space. Soon, the molecules in the space above the liquid establish a vapor phase. As the concentration of molecules in the vapor phase increases, some molecules return to the liquid phase, a process called condensation. Eventually, the number of molecules leaving the liquid is equal to the number of molecules returning to the liquid. A state of dynamic equilibrium is reached as the rates of evaporation and condensation become equal. The difference in mercury levels, represented by H, is the equilibrium vapor pressure of the liquid at the given temperature.
So really, I wanted you to see this just so that you could get an idea of how vapor pressure was created. So liquid molecules evaporate and turn into gas molecules. And then as that gas moves and bounces around, as you saw, it exerts pressure on the walls of its container. In this case, with this apparatus, the pressure of that vapor actually pushes the mercury in this tube up. And we can measure the pressure just based on what this H is. So if we could summarize, vapor pressure is the pressure that a gas above a liquid exerts on the walls of its container. Obviously, the more gas you have, the greater the vapor pressure will be. Okay? So that's what vapor pressure is. It's the pressure of a gas on the walls of its container. Now, the big difference between evaporation and boiling is that when you are boiling, you are at the boiling point. There is a temperature at which any liquid molecule can turn into a gas. And that is called the boiling point. When you are evaporating, only surface molecules can evaporate. So evaporation can occur at any temperature. And that's the key word, any temperature. But only surface molecules evaporate. Boiling occurs at one specific temperature. And when you're boiling, any liquid molecule can turn into gas. So those are the big differences. If you leave a glass of water on your nightstand, the water will evaporate. It doesn't boil because you're not at the temperature at which it can boil. So the surface liquid molecules of that glass of water are what are turning into gas and evaporating, not any liquid molecule in the container. So for this blank here, we'll fill in evaporation. Evaporation. I'd like to do it a different color for you so you could see what I'm writing here. Is the process by which gas molecules are released from the surface of a liquid at any given temperature. And that's why you don't see bubbles when something's evaporating, because the gas is being made at the surface and turning right into a gas. But you see bubbles when you're boiling because a liquid molecule down here may turn into gas. Since gases are less dense, it'll rise up through the liquid. Okay? So boiling occurs at any temperature. And when you have the molecules in a closed container, the vapor pressure will bump in, or the gas molecules will bump into the walls of their container, and the pressure that they exert is known as vapor pressure. Oh. Okay, it's the pressure exerted by gas molecules on the walls of their container. So a quick question for you. Which beaker here do you think would have greater vapor pressure? Do you think the beaker on the left or the beaker on the right? And I'd like you to answer that question in your notes. Which beaker do you believe would have greater vapor pressure? How's sample? Sorry, guys. So just try to come up with an answer to that question. Which sample do you think here has a greater vapor pressure, left or right? Okay? Based on what you saw, based on what we've talked about so far. Okay. Vapor pressure is really dependent upon two things. It's dependent on temperature. Because at greater temperatures, there's more evaporation. And if there's more evaporation, there's more gas molecules, which means there'll be a higher vapor pressure. Oh, I'd like to kind of jot that down also in here. And that may help you with the answer to the last question as well. Okay? Vapor pressure is also affected by the strength of the intermolecular forces. And you probably are aware of what that means here. Stronger IMFs mean they really love each other in the liquid phase, which means they won't evaporate as easily, which means you will get a lower vapor pressure, okay? And again, let's just explain it. So less gas, less vapor pressure, right? If you love each other in the liquid phase, you're not going to leave to become a gas. You'll have stronger IMFs, you'll have a lower vapor pressure. And again, as we said above, a higher temperature means a higher or greater vapor pressure. It's very important that you recognize we have, oh, I don't know what happened here. We have something called standard pressure. Standard pressure is given in different units here. And standard pressure is given as 101.3 kilopascals, 1 atmosphere, or 760 millimeters of mercury. But again, that is standard pressure. Okay, that's SP. If we take out the T, that's standard pressure. And that's given to you in reference table B, I believe. A very significant thing happens. Now, what atmospheric pressure is the pressure of the outside air pushing in. So if you look at this beaker that we're heating, or this Erlenmeyer flask that's being heated over here, as the liquid evaporates, it creates gas molecules on the inside of the container. Those gas molecules move around, they hit the walls of their container, they exert vapor pressure. Vapor pressure is like inside pressure, okay? Well, since we are in a gas environment, there's air around us, there are also gas molecules on the outside of the container, right? So there's all these little gas molecules, whoops, on the outside of the container. Let me just draw a few here so you can kind of get the idea. Doesn't look like it'll let me draw them. So there's also gas molecules around this beaker, and they're bouncing around and pushing on the container. There's air hitting you right now because you're not living in a vacuum, you die. So there's air pushing on you. And that air is what we call atmospheric pressure, that's standard pressure. I call it the outside pressure. It's the outside pressure pushing in. And there's a very significant thing that happens when those two pressures are equal. When the vapor pressure which is the inside pressure pushing out, right? That's the pressure pushing out this way. And the atmospheric pressure, which is the outside pressure pushing in, like this. When those forces are equal, that is when a liquid begins to boil. So we have graphs, we have a reference table that gives us the relationship between temperature and vapor pressure, and it even marks for us, the outside pressure. So this is your table, I believe it's table H as in Henry in your reference tables, and there's 4 different liquids here: propanone, ethanol, water, and ethanoic acid. Propanone is what's in nail polish remover, that's acetone. Ethanol is alcohol, like in wine and beer. Obviously, y'all know what water is. And ethanoic acid is what's in vinegar. Okay, so these are just 4 different liquids. And on the y-axis here, you see vapor pressure. Okay, it's measured in kilopascals, kPa. And on the x-axis, you see temperature in degrees Celsius. So what you should know, regardless of the liquid, is that as the temperature goes up, the vapor pressure goes up. Okay, that's pretty significant. The other significant thing that I want to point out from this curve is that there's this dotted line that runs across the middle of it. That dotted line is significant because that represents atmospheric pressure. That's the outside pressure. That's standard atmospheric pressure. And what we just said on the last page is that when atmospheric pressure and vapor pressure are equal, the liquid will boil. So from this curve, among other things we can do is get the boiling point, or the normal boiling point, the standard boiling point of each of these liquids. Because this is propanone's vapor pressure. When it intersects the outside pressure, that's its boiling point. So if we just go down to the temperature, we will see at what temperature acetone, the active ingredient in nail polish, boils. And the active ingredient in nail polish boils about, what is this, 50, 55, 60, 65, 70, 75. So what would you say, about 61 degrees? That's the boiling point for acetone. Alcohol, again, the active ingredient in wine and beer, drinkable alcohol, ethanol, boils normally at about 80 degrees. Okay, that's why they were able to make moonshine. They would boil off the alcohol and then recollect it to make it more pure. This is our water, and you know pure water boils at 100 degrees Celsius. And vinegar, up here, vinegar boils at about 100, 105, 10, 15, would you say about 118-ish? 117 maybe, degrees Celsius. Okay? So, who do you expect out of this list has the weakest forces of attraction? Which has the weakest forces of attraction out of this list? Based on what we learned in our last unit about in bonding and its relationship to boiling point, or what we just talked about, who do you think has the weakest IMFs? So that's the second question I'd like you to answer for Monday. And then finally, there are, I think I have them here, there are 3 questions under this curve here in your note packet. I'd like you to use table H to try to answer those. Okay? So I think we've already answered the first one. See if you can answer the other 2. And that's it for today, everybody. We'll see you on Monday. Enjoy your weekend. Bye-bye.